Hello, seniors. Yes, I am so sorry we're doing this recorded lecture over the July 4th weekend, technically, but I'm uploading it before the end of this week, and this is finals week of like 2 weeks before July 4th. So you got plenty of time to listen to this thing before the actual July 4th weekend. So don't want to hear it. Thanks. And also, it's going to make you graduate on time. So I explain that in the syllabus. Let's go. Right, so this is chapter 25 from our favorite author, Mr. Quentin Carroll. So going back to the Quentin Carroll book, we're going to start off by like a synopsis of what we already learned in Mr. Shepard's REIE class, and then what we already learned in my digital imaging class. And so that would be the factors that affect exposure at the image receptor. Subject contrast, how is that affected at the, notice it doesn't say in the final displayed image. It always says at the image receptor. And so a lot of REIE content, radiation exposure and image evaluation, a lot of the cause and effect of what's going on with the beam, the focal spot size, the magnification factor, creation of penumbra, elongation, distortion, magnification, all those geometric things. And the KVP and mass, now they affect what's the version of the image that we call the latent image captured at the image receptor. But of course now, with the magic of software, we can tweak it so that the latent image isn't the final say anymore. Basically, the latent image in screen film technology was about it. If it didn't turn into a manifest image that you couldn't adjust from that point on in screen film, well, if it didn't turn into a manifest image that was quality, you had to re-expose. But in the digital age, we get a raw data hitting our detector, and then we can subject that raw data set because it is a matrix of intensities represented by number values. You can perform algebra on it. You can perform quadratic equations on it. You can perform a cubic on it. So the lookup tables, the rescaling, all these software techniques that we covered in digital imaging, that's after we have set certain factors that affect the primary beam and necessarily affect the remnant beam, because the remnant beam is just the attenuated version of the primary beam. And so we're going to run through these quick of all the things in REIE that affected what ends up on the image receptor. Okay. So, and then we're going to dive into the guts of chapter 25 as it pertains to QA/QC, and we're going to talk about absorption and geometric penumbra and how that affects the line pair test tool and ultimately serves as the limit to both spatial resolution and contrast resolution. And in doing so, I'm going to define modulation transfer function. Modulation is another word for oscillating, which should bring to mind a wave, which should bring to mind frequency. So modulation transfer function is, remember in digital imaging, we did frequency processing, and noise is a high frequency object essentially. And so we can apply we can do a Fourier transform and suppress high frequencies, and then do a reverse Fourier transform, and then the noise is eliminated. Well, high frequency modulation is also high frequency modulation or high frequencies are also, yes, we can erase those, but also the pixels are at a certain pixel pitch or pixel size. And so the pixels have a frequency too. And that's where the Nyquist theorem comes in, and that's where modulation transfer function comes in. You can get a frequency so high that it's actually higher than the pixel frequency, and then you can't represent it adequately on your imaging system. That's what modulation transfer function means in a nutshell. You lose the ability to display contrast when objects are smaller than pixels. Okay? So that is our definition of resolution. The overall ability of an imaging system to bring out maximum detail or the most amount of visible information. That's its resolution. It has two components. It's got a spatial component, that is very, very tiny objects, right? Large objects, no problem. You can tell the difference between the liver and the spine, okay? But blood vessels or individual cells of the liver, no, we can't represent individual cells on an x-ray, right? Or even some very, very tiny blood vessels like capillaries. Can we represent those on an x-ray? No. Why? Because they're smaller than the pixels. Okay? So the final resolution of the image is dependent upon additional processing and display factors. Ultimately, it's the quality of your monitor. Okay? Do you have a 2K pixel matrix monitor, or do you have a Ultra HD, as they call it, in Walmart and Target or wherever it is you buy your TVs? Do you have a 4K monitor? Okay. A 4K monitor would just be a 4000 by 4000 matrix. That is the pixels. There are 4000 pixels in rows, but there's also 4000 columns of pixels composing your entire screen. Okay. And remember that the digital image is only a portion of the displayed LCD screen. Okay. So the latent image, which is in the modern digital age, it's called the signal. Okay. We talk about signal to noise ratio. Typically, we want a high signal to noise ratio. That is, we want the signal to be strong while the amount of noise that the image receptor takes on or reports is very, very low. Okay, so high signal to noise ratio. The signal is the intended data. It is the remnant beam represented as stored charges in the DELs or in electron traps, depending upon which system you're using. Okay. Historically, in screen film, the latent image was the unprocessed image embedded in the emulsion. The screen film technology had a silver halide emulsion, and it would actually, when it was hit by X-ray, the silver halide salt would actually undergo oxidation reduction reaction and turn into reduced silver, which is black. It's like silver tarnish is black. Okay. But you couldn't see the image. Even though the piece of film was exposed, you couldn't see the image until you processed it through developer tank, fixer tank, wash tank, and then drying rack. Okay? So altering the chemistry of the emulsion brought out the darkened silver, and by difference we saw where there wasn't dark silver, that's where we saw the bones. Okay, so the image was hidden until it went through our processor. Okay, in the same way, in digital technology, we still have a hidden image. The remnant beam that strikes the image receptor and stores charges until those charges are read out and then processed by algorithm and displayed, it's all hidden image. Okay. Now the term doesn't make sense because implied in the word image is something visual, but the latent image or the hidden image it's like the potential for an image. It's a data set, and with the right equipment, that data set can be interpreted and displayed on a computer monitor as an image. But until it actually pops onto the monitor, it's not a manifest image, it's a hidden image or a latent image. All right, so maximum number of details. Well, what is your medium for viewing? Okay, the modern medium for viewing is the computer monitor, also known as a liquid crystal display, an LCD. Now, the resolution of these things vary according to the quality of the liquid crystal display component and the size of, yes, there's monitor pixels too. So the LCD crystal is divided up into smaller segments. Those are known as the cells of the LCD. And each cell represents a pixel. Okay? And I think they actually nest cells in dot triads, where you'll have one cell is green, one cell is blue, one cell is red, and they just do that with color filters. But that's a red, green, blue pixel, and those are the dot triads. And so depending upon which book you read, which person you talk to, each one individually could be considered a pixel, or all of them together, the blue plus a green plus a red is a single pixel. It really depends on who you're talking to and what your point of view is. It gets even more complex than that, because when we turn it to a grayscale, we don't need color, because essentially our data set is black and white and shades of gray in between. We don't need a dot triad anymore. So a blue pixel isn't a blue pixel anymore. It's just shades of gray. And so is the green pixel, and so is the red pixel. And so the color monitor reverts back to black and white, and the resolution improves. Now, we'll go into that with pictures a little bit later. Okay. The point is not every LCD monitor is the same. There's high resolution and there's low resolution monitors. How much did you invest when you bought these monitors? Native resolution, standard resolution for a hospital display workstation is usually about the equivalent of a 2K monitor, an HD monitor. In the radiologist's reading room, they have the higher class monitors. And we talked about this in digital imaging, I believe, class 1 and class 2 monitors. They have the Ultra HD, the 4K monitors in the reading room. Okay. So that's an important nuance of LCDs. Not the resolution isn't the same for all viewing monitors. Okay, so your imaging system might be broadcasting in 4K or have a image data file that is coded in 4K. But if you're viewing it on a 2K monitor, that's the limit of the resolution you're going to see is 2K resolution. Okay. In addition to that, Mr. Carroll wanted to, after he talks about all this and defines resolution and tells you what things are all about, then he's going to go back and talk about the latent image and what are the influences on the signal or the latent image before we even consider what the final image display looks like. All right, so how do we affect the quantity of, or the signal strength? That is the amount of exposure onto the image receptor. Well, milliamperage is the first and foremost, directly proportional, because milliamperage, remember, is quite literally the number of X-ray photons you're sending in the primary beam. Not by percentage, by count, okay? So, it's like I think I did the calculation one time because I know what the 1 coulomb was like 1.6 times 10 to the 18th electrons. So 100 MA is like um, a tenth of a coulomb. So that's like 1.6 times 10 to the 17th electrons are racing across your tube for 100 MA. But only 1% of those make X-ray photons. So the number of X-ray photons you're making is, divide 10 to the 17th by 10 to the 10 squared, or 100, to get the 1%. And then you end up with 10 to the 15th. So 1.6 times 10 to the 15th photons is how many photons you send with 100 MA, or 100 mass. Okay? I think that's a billion trillion photons. That's what I vaguely recall me doing this calculation. I did it like 2-3 years ago. I think it's a billion trillion photons. Okay. Now, is that what hits the image receptor? No, but that's how many photons are in the primary beam. And then you have a certain percent transmission, and then multiplying the percent transmission by the total number of photons in the beam gives you the remnant beam signal strength. Okay? Exposure at time and milliamperage, ultimately mass, both factors of mass affect remnant beam signal strength in direct proportion because they affect primary beam signal strength, or primary beam intensity, or quantity. Okay. Total mass affects it in direct proportion. It's the prime factor for controlling signal strength. Okay, not controlling brightness, controlling signal strength. KVP affects it in an exponential manner, as displayed by the 15% rule. Type of generator and rectifier used affect it. Okay, so your more efficient generators, remember, less ripple, more constant voltage, and so a increase in generator efficiency is the equivalent of increasing KVP. In a clinical application, protective filtration does not affect it, but compensating filtration is thick enough to it. So what's a compensating filter? Like a wedge filter for a scoliosis series. Okay. But protective filtration, remember, that only stops the low energy X-rays that are never going to make it to the image receptor in the first place. The low energy X-rays that are filtered out protectively before the beam leaves the collimator are only to save entrance skin exposure and guard against entry, because they're so low energy, they're not penetrating, therefore they're going to be absorbed by the patient if we don't stop them before they get to the patient. Okay, but compensating filters, like a wedge filter used for leg length or scoliosis images, can affect remnant beam signal strength. Okay, collimation affects remnant beam signal strength, obviously. Part thickness affects it in an exponential fashion. The thicker the part, the more attenuation in general. Patient condition, pathology, and contrast agents. Well, of course, additive pathologies, hypersthenic habituses, right? And the presence of high atomic number contrast material is definitely going to influence percent transmission, so therefore influence remnant beam signal strength. Scatter radiation. Okay, scatter radiation, it depends on who you ask and what context. It's not, I would say no, it's not technically part of the signal, but it obscures, if scatter radiation is too prominent, it obscures the signal. Okay, and it's the story about the Rockefeller Christmas tree. Okay, So, and I think I covered that in digital imaging. When you go looking for the Rockefeller Christmas tree, it's kind of obvious. Like you go up into the Catskills and you just start walking through the pine forest until you're overwhelmed by the size of a particular. You'll know it when you'll see it. You'll be like, "Oh my Lord, yeah, that's the one." That's the intended signal. The trouble is when the Rockefeller Christmas tree doesn't stand out. When I'm talking about the Christmas tree at Rockefeller Center for all the people who haven't been to New York City. Usually it's like north of 100 feet tall. It's huge. It's the biggest Christmas tree ever, year after year. But when you have too much noise, too much scatter radiation, the signal doesn't really stand out anymore. And so not necessarily the signal strength isn't affected directly. It's just the computer can't identify the intended signal, and because it looks too much like the amplitudes or the magnitudes of the noise as well. And so what it does is it sends both noise and signal, saying, well, all of this is big, so this must be what you wanted. Okay. Anode Hill effect modifies it. We do get a loss of signal strength on the anode side of the image receptor. SID affects it by the inverse square law, and OID affects it because it affects signal to noise ratio because of the air gap technique. Okay. Subject contrast is controlled by KVP. And yes, he spelled voltage wrong. I don't know what the heck happened there. Type of generator, efficiency of the generator is effectively a KVP increase. Protective filtration does not affect subject contrast, but compensating filtration does. Field size affects it substantially. Collimation, if you collimate to a small, that is trim, to a smaller field of view, then you get less scatter events. Okay? If you get less scatter events, you get a cleaner subject contrast. Part thickness affects it because part thickness affects scatter generation. Pathology and contrast agents and patient condition affects it because they all affect scatter generation. So therefore, number 7, scatter radiation levels affect it profoundly. You do not get a true white color if you have excessive scatter. You don't get it because there's always a photon strike. Is it pure attenuation? No, some scatter hit those pixels. And so it can't be pure white. It's got to be off-white, you see? And so your grayscale is truncated and there is no true white with excessive scatter radiation. Grids affect it substantially because they control and clean up scatter radiation before it reaches the image receptor. OID affects it because of the air gap technique. Severe motion can reduce subject contrast because that increases blur. So affect noise present in the latent image. Okay. Insufficient mass, again, that's a poor signal to noise ratio. Insufficient KVP, also poor signal to noise ratio. Large field sizes increase scatter production, so increase the amount of scatter noise. Okay, there are several sources of noise, like it says in the red there. Part thickness, patient condition, grids, OID. Motion can generate false images, but I would say motion is really motion artifact, not really noise. Okay, So difference of opinion between myself and Mr. Carroll here. Positioning can affect it as artifacts or obscuring anatomy can be superimposed over the anatomy of interest. Also not really noise, that's just superimposing artifact. Okay. Sharpness, all your geometric factors. Focal spot size, sod over oid, okay. That controls your penumbra triangle. Sid, sod, and oid all affect it because the penumbra triangle is set by its similar triangles, and the penumbra is a similar triangle to the focal spot size side, and then the adjacent sides, better if I draw it because I'm talking about similar triangles. The adjacent sides is literally the OID to the SOD, okay? And that's where that ratio comes from, is the ratio of similar triangles for penumbra or sharpness. Motion is the prime enemy of sharpness. Motion creates motion blur, which is different than penumbral blur. Motion blur is controllable and preventable to a certain extent, whereas penumbral blur is a function of the engineering of the X-ray beam and the geometry of the X-ray beam. Okay. Exposure time affects it more, I would say influences it, because it allows for the potential for motion. And so motion blur, different than penumbral blur, is more likely to occur with longer exposures. That's just intuitive. If you think about x-raying a 2-year-old, if you give a 2-year-old time to wiggle, will they wiggle? Well, yes. That's what 2-year-olds do. All right. Magnification distortion, again, more of the geometry. Sid over sod is the magnification ratio. Okay. And so the object size times the Sid over sod ratio gives you the image size. Okay. Alignment of the beam part in the image receptor, two parallels and a perpendicular, is the controlling factor for shape distortion. You get the best representation of the object with as little shape distortion as possible if the long axis of the object and the image receptor are running parallel and the beam is directed perpendicular to both the long axis of the object and perpendicular to the image receptor. Your results may vary. Okay, think of any long bone projection. We center to the midpoint with a perpendicular beam, okay, and the image receptor runs parallel to the length of the long bone. Well, that's the geometry you need to minimize magnification and elongation and foreshortening, is you need that specific geometry. The body part and the image receptor are parallel. The center ray is perpendicular to both. All right. So now that we've reviewed what influences the latent image, now we're going to talk about the manifestation of penumbra coded into our image receptor. And there's two types. There's the geometric penumbra, which is classically referred to as edge blur. But then there's also absorption penumbra, which deals with the inherent shape of the object we're trying to image. Okay. And so the perfect shape to image on X-ray is actually a trapezoid, because the trapezoid object, if you center to the trapezoid the expanding beam, the parallax or the spread of the expanding beam oftentimes can match a symmetric trapezoidal shape, and you get a clean edge with I didn't say zero penumbra, zero absorption penumbra. You still get edge blur, you still get geometric penumbra because you have a focal spot size, but you don't get absorption penumbra because the way the beam expands and the way that the trapezoid expands, those expansions are synchronous. Okay? So an exposure trace diagram is supposed to be a visual aid to show you there's basically a ditch here. Okay, it's a carved out ditch. It's supposed to show you the differences in exposure level when you put an object in front of the primary beam. Okay, so the contrast is the depth of the ditch. All right, but the ditch does not have vertical walls. It's got like slanted walls. So there's the true shadow, the umbra, and then the slanted walls represent the blur as the object's attenuation is fading because it's got a edge that you are not mapping to a single location on the image receptor. You're actually spreading out that edge over basically something proportional to the focal spot size times the OID over SOD ratio, OID to SOD ratio. Okay, so we end up with, instead of a true shadow, which would just be an attenuation map or a ditch where the object absorbed the exposure rather than the image receptor absorbed the exposure. So you got to make that clear. The hashed area is representative of exposure to the image receptor. So it's how many photons landed on the image receptor in locations. Because we have an object in front of the image receptor between the X-ray tube and the image receptor actually caught less radiation immediately behind the object. That's what the ditch means. There was less exposure immediately behind the object. But when you get to the edge of the object, there's a gradient of exposure from the true shadow back to full exposure. Okay? This gradient is the penumbra. It's the edge blur. It's the fuzziness in the edge of the object. The object just doesn't come to a sharp stop. It kind of fades. Okay. All right. Now, absorption penumbra deals with fading of the true shadow because of the variation in thickness of the object itself. You see a sphere. If we look at example C, the sphere, because it's got the worst absorption penumbra. Remember I said the trapezoid was the best true edge? Well, a sphere is the worst. So let's look at the sphere. Notice that going through the center of the sphere, the X-ray goes through the actual diameter of the sphere. And so the attenuation there is 100%, I guess, or 80%, right? But every slanted pathway away from the center, you're going through less linear distance of the object until you get to the edge and you're barely going through any of the sphere at all. And so what happens is the attenuation fades gradually and spreads out over a longer area or a wider area on the image receptor. So it's it's not a stark change, it's a gradual change. So spheroids are always a smooth transition from highly attenuated to, at the edge, poorly attenuated. Versus trapezoids provide the best umbra or true shadow and the best contrast to Okay, here's definitely the edge of the object. Okay, with a spherical shape, the absorption penumbra and the tapering of the object from its true diameter, the X-rays are going through less and less of the object in a linear distance, and so there's less attenuation in any point of the sphere except for the center. The center is the point of maximum diameter, therefore maximum attenuation. Okay? The square is roughly halfway between. The trapezoid is at one extreme, where you get a very high contrast and almost zero absorption penumbra. The sphere is the worst example of absorption penumbra. The square or the rectangle has slight absorption penumbra. It's like the halfway point between the trapezoid and the sphere. All right, so we get different exposure trace shapes based on the different objects. The trapezoid is going to radiograph best. That is as far as its spatial resolution goes. And its subject contrast relative to its environment. The squared object is going to have, see how the dashed line or the dotted line kind of maps out a triangle. Anything in that triangle, you're not going through the full distance of the square, and so you start to see a fading of attenuation, or the attenuation character of the square is weakest at its edges, is another way of putting that. Whereas the sphere goes through a gradual weakening of attenuation because it's constantly tapering to its edge. It is a gradual absorption penumbra and a low contrast change rather than a high contrast change. All right. So again, because we have different shapes, we get different exposure trace diagrams. Okay? And so this is showing you how the object itself can affect your subject contrast in your latent image. Okay? And he just tells you exactly what I just told you. The sharpest edges are the trapezoid. Absorption penumbra in a square object produces basically another region similar to a geometric penumbra. And then absorption penumbra in a spheroid creates a low contrast transition, which is even worse because it makes it more difficult to see. Excuse me. Okay. So this is a hybrid diagram showing you both geometric penumbra at the edge manifested by the vertical triangles at the focal spot. So you can see the apex of the vertical triangles is at the edge of the square there with the solid line diagrams going back to the focal spot. So the source of the geometric penumbra definitely is the focal spot. The girth or the width of geometric penumbra is the focal spot size times the OID to SID ratio, okay? Which are the lengths of the other sides of those vertical triangles. The dotted line refers to absorption penumbra, in which the distance through the square at the top corner is minimal, but gradually increases until you get to the bottom corner where it comes to a maximum. Let's say that square is 1 centimeter thick. Well, only at the dashed line is the X-ray actually going through 1 centimeter of object, roughly. Yes, I know it's still angled, so it's not really, it might actually be more than 1 centimeter because that's the hypotenuse, not the length of the side, Mr. Tilton. Yes, I took trig, I understand. Okay, but the true shadow is in between the bottom corners. The false shadow is the projection of the geometric penumbra, the outer edge of the geometric penumbra created by the top corners. Okay, so the total penumbra is actually the sum of the geometric and the absorption penumbra, which for a square is, I mean, it's halfway between trapezoid and circle or spheroid. All right. Overall image resolution, the ability to distinguish individual parts of an object or two separate, very, very small objects that are adjacent to each other. All right. All image qualities combine to form the overall resolution, which really isn't. But you can't really wrap your head around resolution. Okay. When you really think about it, there's this thing is definitely black. That one over there is definitely white. That would be contrast resolution, your ability to distinguish two objects because they display at two different colors. And then spatial resolution, I can tell that this is object 1, which is a square, and that object 2 is object 2, which is a circle. And the reason I can do that is because I can identify their edges, and they have well-defined boundaries. That's spatial resolution or sharpness. Okay. So the trouble is when we get to the very, very tiny, you only identify shapes by their edges, and you only identify edges by contrast. And so spatial resolution is dependent upon or limited by, as a mathematician would say, contrast resolution. A high contrast image and still have motion blurred edges. So you would lose spatial resolution. A sharp image can still have poor resolution if low contrast, that is the color difference between the two shapes, is negligible. How would you even, like if I took black construction paper and I cut out a square, and then I took the same piece of construction paper, just another section of it, and cut out a circle, and then I put the square down, and then I put the circle down on top of the square, the circle fit inside the square, from across the room you wouldn't even know that there was a circle piece of paper there. It's because they're the same shade. They're the same color. Okay? So objects that are the same color, think about like your hyperesthetic abdomen and trying to distinguish the liver from the right kidney. It gets trickier as the patient gets bigger. That's because you're losing contrast resolution. You can't find the distinct edge of the kidney because everything kind of looks like the same noisy gray in that right upper quadrant. You also don't see the lower diagonal border of the liver on that radiograph too, if you're being honest with yourself. So spatial resolution is measured by spatial frequency. Now, this is a pet peeve of mine, and I think I dedicate a slide to this. Spatial resolution and spatial frequency are not the same thing. Spatial resolution is a subjective term. Spatial frequency is an objective measurement. Okay? Spatial frequency is measured in line pairs per millimeter. Spatial resolution is either good or poor, or better or worse. You see the difference? You can only quantify one of those, and that's spatial frequency. Contrast resolution is measured by modulation transfer function, which is how well do we transfer frequencies? What? Well, let's go back to think about frequency processing. Remember we said high frequency objects were bright pixel, dark pixel, bright pixel, dark pixel. Well, that's a line pair. Okay, so that's a high frequency line pair pattern. What I'm suggesting to you is we can create a phantom that has lead strips with interspace like a grid, okay? But we can put those lead strips so close together and make the spaces between, make the thickness of the lead strips smaller than the width of a pixel. And then make the inner space also smaller than the width of a pixel, and you won't be able to radiograph the difference, even though you can visually see that's definitely lead, plastic, lead, plastic, lead, plastic. If it's smaller than the width of your pixels in your imaging system, the X-ray machine is not going to be able to demonstrate that. It's just going to demonstrate a gray blur. In other words, it loses the ability to transfer an actual frequency, that is, an object frequency, and display it as an image frequency. In other words, it's a modulation or frequency transfer function. Okay? So you see the line pairs on your monitor right now. But if you're viewing this on 2K, full screen, I'm going to read it off on mine, and you'll see if your monitor is better than mine in my office. The last one I can clearly see is 1.88. I can see white interspaces in between the black lines. When I get down to 2.09 line pairs per millimeter, it's all smeared together. So that tells me my monitor resolution is roughly 2 line pairs per millimeter. Because once we go beyond 2 line pairs per millimeter, I can't make out individual black lines anymore. So just look at that yourself as you're listening to the recorded lecture, and you'll be able to measure the spatial frequency of your monitor and see if you have a 4K monitor. You should be able to see up into the high 2s, maybe even up into the 3s. I'd be interested to know if anyone does have a 4K computer, if they can, what number of line pairs per millimeter were you able to see? Okay. So this is actually a radio opaque standard, and I have one of these. I think we do a lab on it. I'm not sure. There might be time for a lab on it. I hope there is, because it's a very fun lab, where this is actually a piece. It's a slab of plexiglass plastic, and it's got lead strips embedded into it. And so you can actually X-ray it, and then you can figure out the resolution for your imaging system, which again is limited, as Carol points out, by the quality of your monitor. And so ultimately, your imaging system comes up with an upper limit to its spatial frequency that it can broadcast without blur. Okay, and that limit is set by the modulation transfer function. Okay, what you're losing is contrast resolution. That's why it appears to be, we're measuring spatial frequency, which is the quantification of spatial resolution, but it's limited by contrast resolution, that is the ability to display a black line different than a white line. Okay, and when those lines get closer together than the width of a pixel, then we can't display them as individual objects anymore. We merge their attenuations and blend it into a single attenuation, because a pixel can only display one shade of gray. All right. So this is also related to the Nyquist theorem. The Nyquist theorem states that um, sampling frequency must be twice input signal bandwidth. What that means is there is a limit to the spatial frequency that you can record with an imaging system. That limit is the Nyquist theorem. Your pixel size, you need 2 pixels to create a line pair. If the object has a line pair that is smaller than 2 pixels across, then you won't display, when you take an image of that object, you won't display that line pair. As long as the object is greater than the size of 2 pixels across, then you'll be able to display it adequately. And again, my resolution tops out at 1.88. Okay? And the reason is because my pixels are exactly the size of the 1.88 line pair. So it's 1 pixel for the black one, and then the white one immediately below it is the next pixel. Okay? Versus if I go to the 2.09 line pairs per millimeter, now some of the white is on the first pixel rather than on its own pixel. And so the colors are blended together. And so our ability to transfer the frequency from the actual object to a representation, to an image, has broken down. In other words, we've lost modulation transfer. Okay, so let's take this back to an exposure trace diagram. What is that going to look like? Because the line, the object that is the line in this line pair test tool, that's a strip of lead, okay? And so it's going to create, it's a rectangular prism, square on the one end, and then it's got a long axis to it. So in cross section, it's going to look like the exposure trace diagram for a square, okay? What happens when you bring this exposure trace diagram really, really close to the next one? Okay. So resolution fails because what happens is if you bring 2 square exposure trace diagrams close together, eventually their penumbras, their edge gradients overlap. And that's where modulation now there's not a distinct unexposed gap in between the 2 pieces of lead because it's being filled in by the penumbral gradient. Okay, and so bringing 2 exposure trace diagrams in toward each other, eventually those penumbral gradients, those edge gradients, touch and overlap, and then you lose a raw primary inner space in between. It doesn't map the inner space correctly because the penumbras are overlapping with the inner space. Okay? So a physicist would say that resolution is both contrast resolution, that is, can you distinguish between 2 different objects because they're different colors, and spatial resolution, that is, can you identify a shape or an edge to an object? Okay. The radiographer, because the physicist is only thinking of it in terms of the geometric factors and like the abstract concepts, okay? But the technologist, it's a little bit more complex for the technologist, because the technologist, yes, we have visibility, which is contrast resolution and spatial resolution, but we have subcategories of those that are influencing, like contrast resolution is influenced by the overall brightness of the image or the overall darkness of the image. Contrast resolution is influenced by our LUT and our gamma. Contrast resolution is influenced by the amount of noise that is present in our image. Spatial resolution is influenced by, so recognizability, now he calls that geometric integrity. The ability to see an edge is affected by overall sharpness or geometric penumbra, magnification, okay, and elongation. And so why is the radiographer's image quality so much more complex, and that analysis so much more complex? And that's because we're assigning diagnostic and anatomic meaning to the objects. We're taking it a step farther than what the physicist is considering. The physicist is only considering, on the one side, are the two objects two different colors on the image? And then does each object or one object have a distinct form? That is, can you see its outline? Okay. So it has correlation, but we take it further and assign more meaning to it, and we assign root cause to it, and we acknowledge influences on it, more so than just arbitrarily looking at just the difference in colors. Okay, what is affecting those differences in colors, and can you see a distinct edge versus what is affecting our ability to see that distinct edge? All right, so you need to understand what the physicist is talking about. That doesn't mean it's not true. It's just more abstract than what is practical for us in terms of image quality. Okay? Yes, the physicist is correct, but we need to add more to it, because there's a more, the whole point of chasing good contrast resolution and good spatial resolution is overall image quality. Whereas the physicist doesn't really have a goal in mind. He's just interested in an objective measurement, so to speak. So the modulation transfer function is the breakdown of contrast resolution that leads to a loss of spatial resolution, as I said before. And I think this is what the take-home, it says in class exercise, but we got messed up by the July 4th holiday, so it's going to be a take-home exercise. Disregard the in-class part. Definitely do the homework that I assigned. Okay? So we have a line pair test tool. Okay? And then we have an image of the line pair test tool. By visual inspection, if we actually have this line pair test tool and we're holding it in our hands, we can see that it is a sheet of polymer plastic and it has metal strips embedded in it, so that it has an alternating pattern of highly attenuating material or radiopaque material, radiolucent material, radiopaque material, radiolucent material. That's what we would call a line pair. Okay. When we take an X-ray of it, we get black stripe, white stripe, black stripe, white stripe. Okay. We understand that the black stripe represents radiolucent and the white stripe represents radio opaque. Okay? But there's a problem. Our imaging system is not perfect, because if it was perfect, we would see all the way down to 4.86. But there's a problem. We start to lose the ability to see the alternating strips of metal in between the plastic at about midway down the pattern in our image. Okay? So if let's say, okay, well, we're going to resurrect Nick Tesla, Albert Einstein, and Godfrey Hounsfield, and we're going to say, look, gentlemen, we want a perfect X-ray imaging system. And so they said, well, we just need to make the pixels smaller. And Einstein said, well, you would need a quantum image receptor for that. And Tesla says, yes, that's right. You would need an electron acting as the pixel. And so Hounsfield said, well, it's going to be tricky, but I think if we follow Moore's law with what they're doing with transistors and jump into quantum computers, we might be able to build a model for a quantum detector that could measure not necessarily the electron as the pixel, but the ionized atom itself as a pixel. And so we would get a different electric field coming off of that atom that was ionized. And so that would be a different magnetic field. And so with a very, very sensitive instrument, detecting small undulations in the magnetic field, we can actually map when a individual molecule gets ionized by a photon, and we could create an atomic, a pixel that was effectively an atom. And if the atom's in a ground state, then that's considered radiolucent. But if the atom becomes ionized and we detect a disturbance in its magnetic field, then that is considered to be attenuating or radiopaque. And so theoretically they put their heads together, but it still takes about 3 years to get the technology and the engineering to catch up to the theory. But then you finally do it, and you get lines that are literally one atom across, and you represent the test tool completely. That would be an MTF of 100%. That would be a perfect imaging system. That would be an imaging system so good that the actual object and a picture representation of that object would be indistinguishable. It's kind of like the perfect hologram, if you would. Well, needless to say, none of our imaging systems have a perfect modulation transfer function or a perfect image. There's always a flaw in the image where it's a close representation of the object, but not exactly the object. All right, so this is what I was talking about with the overlapping penumbras. You see those edge gradients are really, really close together, but I can still see a small sliver of full exposure in between them. But if I bring those radiopaque objects any closer together, the penumbras will overlap, and I won't get a true white in between them. And so I will lose my ability to display radiopaque, radiolucent, radiopaque, radiolucent, an alternating crest, trough, crest, trough, crest, trough. That is, I will lose, the frequency will get so high, the object frequency will get so high that I'm not sampling it enough. I'm reaching the Nyquist limit, and my contrast resolution breaks down as a result of not sampling enough versus the object's high frequency. All right, so modulation transfer function. Our object has a frequency. It's got a frequency of radiopaque, alternating radiopaque and radiolucency. That creates an exposure trace diagram that looks kind of like a sine wave. Okay, but as those lead strips get closer and closer together, our ability to represent a true crest fades because the edge gradients start to overlap. Okay? When that point happens, we've met the Nyquist limit and we've lost the ability to transfer the native frequency of the object to the image. We've lost modulation transfer. Okay? Right? Now, why does this happen? Well, because we're encoding penumbra into the image. Remember, penumbra is the false edge. It's not really there. But we can't really do anything about it. When we record an object with an X-ray, we'll always generate a false edge. Okay? This false edge always leads to a breakdown in contrast resolution if the objects are small enough and close enough together. That's essentially what modulation transfer function and the Nyquist theorem are saying. Okay, so increasing the frequency, eventually you get penumbra overlap and you don't get a true peak. And remember, the peaks represent radiolucency. And so you don't really display radiolucency and you lose the ability to display two different colors at that point. Okay? So that's the loss. That's why these line pairs, if you're being honest with yourself, that's not white, that's gray. We're already seeing the penumbra bleeding into the inner space, or bleeding into the lead strip, so to speak. Whereas on this other side, we still have sharp edges. Okay. All right, that was the end of that. All right. So we talked about a quick review of factors that influence the nature of the remnant beam and what's striking the image receptor. Okay, and then we did a deep dive on penumbra, exposure trace diagrams, and how when you have a high frequency, the exposure trace diagrams coupled with a high frequency pattern leads to a loss of contrast or a loss of contrast resolution. Modulation transfer function is the ability of our imaging system to display the object and it's in its proper contrast resolution. Because imaging systems have trouble with tiny objects in close proximity, we never get a perfect imaging system. We never get a modulation transfer function of 100%. Okay. This loss of contrast resolution also is a loss of spatial resolution. Because remember, spatial resolution is the ability to see an edge, and it's literally the edge that is breaking down or overlapping with the next adjacent edge. All right, that's all we had for week 1. I will see you guys. I think that's July 11th is the next class. Yeah, I'll see you guys for week 2. Take care.